Hi guys, happy Tuesday. So today we're going to be talking about elastic potential energy, but this time we're going to be applying it to a lab situation. So specifically we'll be looking at a pinball machine. We use springs often in cars and pens. So technically your pens that click, right? Each one of those pens contains a spring. That spring allows the point of the pen to be retracted or extended, so that you're able to write. Another common use for springs are within arcade games. So even the earliest pinball machines, which date back to the 1930s, use springs to create motion within the machine. So basically, even though the pinball machines have drastically advanced since the 1930s, right now we have lights and themes and colors and multiple levels, even little boundary buttons, okay, that we can use to shoot the ball back into the actual maze. Even our current pinball machines rely on springs, okay, and the fact that springs can store elastic potential energy. So we're going to be taking a look at this transfer of elastic potential energy to kinetic energy through a life-sized pinball machine. Okay, so last paragraph in the background information is where I'm focused on here. So basically, Trevor, who is a hockey goalie, is going to be shot across the ice after a spring is released. We know that ice is theoretically frictionless, so that means that no energy will be lost as heat. If no energy is lost as heat, that means that all of the elastic potential energy stored in that spring will be converted to kinetic energy. So that compression, that energy will be directly related to kinetic energy, meaning it will influence Trevor's velocity. We're going to specifically examine how Trevor's mass, the spring constant of the spring, the compression distance affect Trevor's speed, as well as looking at the fact that elastic potential energy is directly converted to kinetic energy while we're on that frictionless surface. Okay, so on the bottom of that background information here, you see a little scheme, a little drawing. Okay, so I'm just going to generally give you an idea of that life-size pinball machine that we're going to be exploring. So you see on the right-hand side of this image here, we have Trevor, who is in front of a spring. So Trevor is going to compress that spring. You guys get to choose the compression distance for some of the parts, okay? And you'll see that in a second. So you choose the compression distance, and then you fire Trevor off across the ice. Okay, there's a region on the ice in which we call the neutral zone, and that is the displacement between those two blue lines. In the simulation, it shows you that that displacement is exactly 18 meters, and there's a timer tool that lets you time Trevor's motion. Specifically, we want to time how long it takes Trevor to move through the neutral zone, through that 18-meter displacement. So as soon as Trevor crosses that blue line, you're going to press start. As soon as Trevor approaches that second blue line, you're going to press stop. Okay, so you can head to the next video explanation for part 1. That's the end of the background info.